Okay, so what is momentum and impulse? So momentum, let's look at the equations first. So momentum is P equals mv. And v. So if we just remember this equation, which we don't actually need to remember because it's in the equation sheet at the back of the book, from this we can get a bunch of things. One of the things we know is then we know the units of momentum, which is mass we know is kilograms, and velocity is meters per second. And then from that, we can also get the definition, because often what they'll do is to start off a question, they'll say, define momentum. And then with that, what they're doing is also telling you what equation you're going to be using in that question. So it's a good way of knowing, okay, this question is about this. So sometimes they'll say, define Newton's law, Newton's second law. And then if you hear Newton's second, you know, okay, they might be dealing with momentum, and we're going to be using the force equals mass times acceleration equation as well. So those definitions we've just got to learn. But if we just look at the equation, you don't necessarily need to learn the definition off by heart, because I remember one of my science teachers said a definition is usually an equation. So the definition of momentum, you just use the momentum equation. So you would say momentum is the product meaning times, because we see times, product of an object's mass and velocity. To get full marks for this question, we would also need to make sure, because we know mass is a scalar, but velocity is a vector. Remember that when we did vectors and scalars last week, speed was a scalar, velocity has both magnitude and direction. So what we would do is, just to get the full marks, is we'd say is a vector quantity, is a vector. So let's just say okay. So that's momentum. And momentum, if we just think of it logically, think of a ball rolling along, okay, or a car rolling along. What would you need to stop that car? Well, that car has momentum, and so you need a force to stop it. And the force that you would need would be based on how heavy that object is, so its mass, because if it's a heavier object, like a car, it's going to be harder to stop than a ball. And its velocity. So if the ball is being thrown at a huge speed or velocity, it's going to take more force to stop that object. So that is momentum. Now, when they ask you about impulse, impulse is very closely related to momentum, because it's even though it's got different units, technically they're the same, they're measured in the same units, but we just write them as different units. Sounds a bit confusing, but let's have a look. So impulse is equal to my change in momentum. Change. So sometimes when they give you the momentum, you then know that you need to work out the, to work out the impulse, you can just get the change in momentum. Now let's look at the other definition, or the other equation that they use for momentum, and that is, impulse, and that is force. So we'll do force times, times, I haven't used purple yet, times change in time. Okay, so when you think, I don't know if you play cricket or tennis.
I've played it.
Which one?
Yeah, I've played cricket and tennis.
Oh, perfect. Okay, so often when you want to sort of hit a powerful shot, you're always asked to kind of follow through when you play the shot. And that is because you want to maximize the contact time that the racket, the bat has with the ball. So because your force is still the same, you're still applying your mass times acceleration. So the mass of the cricket bat times the acceleration that you are causing that bat or the racket to move. So that's your force. But if you can follow through and increase the time that your bat is in contact with the ball, you're going to get a greater impulse and it's going to fly further or faster. So now we could also get a definition for impulse. So we know that impulse is the product, move this up here, of the force over the time interval. That an object experiences the force moment. Okay, so that could be a definition. Definitions you can learn. You've got the book, but rather than learn them, just check the equation. And when you're learning them, think how they apply to the equation. And so in that way, you cut down your learning time, because you're not really learning. You just actually understand, which is obviously what we want to do. So those are the equations. Let's look at the units quickly. And then what I'll do is I'll stop this and we can do some examples perhaps. So let's look at, we've done the mass. I wanted to look at the units of impulse. Okay. So we know that force is mass times acceleration. So force is here, mass. So force is mass times. So we'll do that in orange. So mass is kilograms. And then acceleration is meters per second squared. So what I'm going to do is I'm going to put the seconds per second. I'm going to put the s squared at the bottom, just for the explanation part. Okay, so remember force, mass times acceleration, such as weight, so which is your kilograms, and then the acceleration towards the earth. So that would give you the weight, which is a force. Now we also know that force is in newtons. But I just want to show you how it relates to momentum first. And then time is in seconds. So times s. And we see that what we can do is we can cancel this s with one of the s's down here. And we get kgs, meters per second, which is exactly the same as this units for momentum. So they are the same units, but we don't express them in the same units. The units we express momentum and impulse in are Newton seconds. Okay. So that can be quite confusing because they're expressed in different units, but they are very closely related. So your impulse is your change in momentum. Last thing I'm going to say about momentum is it's always conserved. So often you'll get like a multiple choice question and they'll say like they'll talk about kinetic energy and all that with momentum and which is conserved. You know, momentum is always conserved. Okay, so when in doubt, momentum is always conserved. I'll just write that down quickly. Momentum is always conserved. And this has to do with the collision question. So you'll have two cars or two objects moving, one moving in one direction and the other moving in another. They collide and they maybe go off at different directions, or they attach and go in the same direction. You know that the momentum is always conserved. So we'll do an example of that. But then kinetic energy is a thing that's not necessarily conserved. It's only conserved in an elastic collision. But we'll go through that next time. So I'm going to stop it there.